Good day all, I remain Dr. Omali Paul, bringing scientific theories to real-world application. Today I'm going to be talking about harmonics and overtones in a stretched string, that is the second overtone. The wire can also be made to vibrate in 3 loops or segments as shown in the figure. From the diagram, we have the next higher notes after the first overtone called the second overtone or the third harmonic. From the diagram, your length L is going to be equal to 3 lambda over 2. That is your equation 1. Also, from the formula, V is equal to F lambda equation 2. When we make F the surrogate formula, we're going to be having F is equal to V over lambda. This is equation 3. Also, from equation 1, 3 lambda is equal to 2L. While lambda from that equation is going to give you 2L over 3 as our equation 4. So substituting equation 4 into equation 3, we have F to be equal to V over 2L over 3. So by the time you resolve that particular operation, your F is going to give you 3V over 2L as your third harmonic or second overtone. In summary, the fundamental frequency is the lowest frequency but the strongest audible frequency, while the overtones are higher frequencies but are quieter and softer than the fundamental notes. When you strike a drum, pluck a guitar string, or blow into a wind instrument, the object or air column vibrates. These vibrations do not just happen randomly, they often set up standing waves. A standing wave is a wave that appears to stand still with fixed point of no displacement, that is the notes, and points of displacement, that is the antinote. The way an object vibrates is constrained by its physical properties, that is length, tension, density, shape, etc., and boundary conditions, e.g. fixed string, open or closed ends of pipe. For any given vibrating object, there are specific discrete patterns of vibration called normal modes or natural modes. Each normal mode corresponds to a specific frequency at which the object can naturally resonate. The simplest and lowest frequency mode of vibration is called the fundamental mode. In this mode, the entire object vibrates as a single unit. For a guitar string, this would be the string vibrating as a whole with nodes and both ends, one antinode in the middle. In addition to the fundamental mode, we have the higher frequency modes where the object vibrates in segments. These are called the overtones. For example, a guitar string can also vibrate in 2 halves, 3/10, and so on, each producing a higher frequency. When the frequencies of the overtones are whole number multiples of the fundamental frequency, they are called harmonics. For instance, if the fundamental frequency is F, the harmonics will be 2F, 3F, 4F, etc. 2F is the second harmonics, 3F the third, and so on. The fundamental itself is considered the first harmonic, that is 1F. Most musical instruments produce sounds where the overtones are largely, though not always perfect, harmonic. This series of related frequencies, fundamental plus harmonics, is known as the harmonic series. Dominant vibration. When a musical instrument is played, the energy transferred to the vibrating object often excites the fundamental mode more strongly than the higher overtone. This means the fundamental frequency typically has the largest amplitude and thus loudness like the initial sound. Pitch perception. The human ear and brain are wired to perceive the lowest frequency component, that is the fundamental, as the pitch of sound. If some overtones are individually louder than the fundamental, which can happen in some instruments like a trumpet or under certain filtering conditions, our auditory system integrates all the frequency components into a single perceived pitch, which is predominantly determined by the fundamental. Timbre, that is tone quality. While the fundamental determines the perceived pitch, the presence and relative amplitudes of the overtone both harmonic and non-harmonic, are what give a sound its unique timbre or tone color. This is why a guitar and a piano playing the same notes, same fundamental frequency, sound different. They have different overtone structures. In conclusion, the fundamental frequency is the lowest frequency at which an object can vibrate, and it's the primary determinant of the perceived pitch. While the overtones add richness and character to the sound, the fundamental is generally the most prominent due to its inherent vibratory mode and our auditory system's processing. Science isn't just in textbooks, it's all around us. Like this video if you find it interesting, and subscribe for more explorations of science in the real world. Thank you.